All right, so now we're going to prove the principle of mathematical induction. So basically, you have some statement P of n that's dependent upon n, and we're just going to say that true is 1 and 0 is false, okay? So basically, we're saying that if you have these two conditions that are met, so here's the first condition and here's the second condition, right? This is condition 1, and then this is condition 2. Now, if you have these two conditions met, that P of 1 is true, right? P of 1 equals 1. And you have the fact that if P of k is true, then P of k plus 1 is true for all k. We got to add this for all k. For all k greater than or equal to 1. Yeah, if this is true for, all right, so yeah, then we're going to have that P of n is true for all natural numbers n. Now, the proof is going to be a proof by contradiction, so we're going to assume otherwise. Assume that these two things are both true, but P of n isn't true for some natural number. Assume that P of n is false. Okay, or P of n equals 0 for some natural numbers, or natural number. Okay, then by the assumption, the set S, okay, is equal to, let's say, I don't know, M, okay, contained in the natural numbers such that P of M equals 0 is non-empty by the assumption. It's not empty. There's elements, at least one element in this set by the assumption. But then, since this set is non-empty and it's a set of natural numbers, what you have here is you have, by well-ordered principle, there must be a smallest member inside S, right? Because it's a set of natural numbers. So any non-empty set of natural numbers must have a smallest member. So there exists I don't know, M, N, what should we do? Not K or M. Not N. What's a good one? There must exist, I don't know, A, that is the smallest in S. Okay. Now, consider, right? And you just really want to literally like consider A minus 1, okay? Or P of A minus 1, better yet, right? So if we consider P of A minus 1, we know that P of A minus 1 must equal 1. Why? Well, we know, first we know that A does not equal 1. So A minus 1 is contained in the natural numbers. That's important, right? So now when we consider P of A minus 1, right, we have to say that P of A minus 1 equals 1. Why is that true? So P of A minus 1 must equal 1. Well, why? because this here, S, is the set of all natural numbers such that P of M, any natural number that gives you 0 is in this set. Okay? Any natural number that P of M, any M such that P of M equals 0 is in this set. Now, this is a set of natural numbers. There must exist a smallest member called A. So A is the smallest one, where P of A equals 0. Okay, because A is in this set. So then, and you have it that P of A must be 0. Now, and A is the smallest, with P of A giving you 0. So A minus 1 is smaller. Okay, so it must be that P of A minus 1 equals 1. But now, okay, P of A minus 1 implies from this here, right, that P of A must equal 1 as well. And this is a contradiction, okay, because we have that if you have it that, right, P of A minus 1 plus 1, right, okay, this is like A minus 1. And then if you do P of A minus 1 plus 1, you just get P of A. So then that forces it to being 1. And now you know that P of A equals 1, but we just said P of A is 0, and this is a contradiction. And you could write the contradiction symbol, and then you can say that the assumption is false. Assumption is false. And you want to state the falsity of the assumption because that's going to be the conclusion. Assume that P of n is false for some natural numbers n. Okay, so now we know that this is false. P of n is true for all natural numbers is the opposite, right? And that's the conclusion, that P of n equals 1 for all natural numbers, for all the symbol all, for all n, for all natural numbers. And now you're done.